fan. And like this, you can increase our objective, the bypass ratio. Maybe here you can reach a bypass ratio of 15 at least. 15, 16, 17. And with the increase of the bypass ratio, of course, you decrease the TSFC. You increase the thrust, and you decrease, of course, the specific thrust. This engine is, let's say, the third turbofan type. This is what is called the GTF, the geared turbofan, because there is a gearbox. And so you see, what we have drawn here is not really existing. This is the idea. This is the idea. But the first one you have, this is the 3-spool engine. The first one you have, maybe not historically, but the first type you can have. This is the 3-spool engine made by Rolls-Royce. Then you have the 2-spool with a booster, what we call today a low-speed booster, because we have a solution with a 3-speed compressor with a high-speed booster with a gearbox that is called the geared turbofan. And these are the 3 types of engines you can have with this double flow compressor, with this turbofan, with the objective always, always, always to decrease the TSFC, decrease the TSFC. So we are now going lower than 0.3 kilo per decanewton hour, and 0.3 kilo per decanewton hour, in order to speak in terms that everybody can understand, this is corresponding with less than 3 liters of fuel per passenger per 100 kilometer. So less than 3 liters of fuel per 100 kilometers per passenger. So if you want to be better than this in a car, you need at least to be 2, but even most probably 3, because depending on the traffic, you will be most probably at a consumption higher than 6 liters, higher than 5.5 liters per 100 kilometers. So we have reached fantastic values of the bypass ratio, fantastic values of the P global, fantastic values of the TIT, and very strangely, lower and lower values of the PF. Because the PF, when you increase the bypass ratio, you reduce PF. So it's not that you want to increase PF. You say, no, less, less, less. So you want to decrease the value that you have there. And then you could say, but why is it so difficult to make that? Because this cycle is even looking as easier than the turbojet. Where is the difficulty? Where is the difficulty? This is in the construction of this. This is the difficulty, the construction of the fan blades. Why is it a problem? Why do you have a problem in the construction of the fan blades? So what's happening? You have a disc, a certain, let's show it like, let's say it's a hollow disc, because it's put on a shaft. So it's a hollow disc that you are installing by different mounting techniques on a shaft. And on this disc, you are putting a blade that is longer and longer. What is the problem? You are also, when you increase the diameter, you are decreasing the rotational speed. Otherwise, you will have too large centrifugal stresses here. Okay? But at the same time that you are doing that, if you take this blade and if you compute the natural frequency of this blade, or the resonance frequency, it will be proportional with the square root of the stiffness divided by the mass. And when you increase the length, if you take ISO technology, what will happen? The mass will increase and the stiffness will decrease. So the ratio stiffness divided by mass will decrease even more. And so you see that you have a large decrease of the resonance frequency. But what's happening? By decreasing the resonance frequency, as you are also decreasing the rotational speed, it's quite possible that these two are in the same range, or that you have even this rotational, let's say, natural frequency higher than this one, and that you need to lower than this one. And so when you are increasing the rotational speed, you need to go over this value, and you could have resonance when you are accelerating the engine. And so the combination of a low resonance frequency and a low rotational speed can become a huge problem. And how can you solve this? How can you solve this? You need to put omega n higher than n1. I know it's not the same unit. This is radian per second, but n1 with that you write 2p n1 divided by 60 in order to have radian per second. But you need to have the rounds per minute of the resonance frequency that must be higher than the the rounds per minute of n1. And how can you do that? There are two ways. You need to increase k. It's difficult because when you increase the length of the blade, k is a trend to decrease. And you need to decrease m, which is also very difficult because you increase the length, so it should be heavier. There are different techniques in order to do that. One of the first techniques that has been selected, this is by putting what is called snubbers here. You see, at this fin that you have on the blade, this fin, this side of the fin is going against this side of the fin of the next blade. And like this, you are, by the contact you have between the different blades, not 30 individual blades, but you will have one single blade that is much increasing the stiffness of the solution. Of course, this is not ideal as a solution because you are increasing the, let's say, contact surface you have between the flow, the air, because it's a compressor, and the blade. And this solution has the trend, in fact, with the snubbers, this is called snubbers, you have the trend to decrease the isentropic efficiency of the compressor. But it's solving the problem of stiffness of the blade, not the mass, because the mass is the trend to increase. So you are just playing with a better stiffness, not with a lower mass. And after this, let's say, small improvement, a small solution, the big players, the big companies, they have invented two technologies in order to increase K and to decrease M. There are two technologies available on the market. The first one, this is to build a blade that is, let's say, empty. This is what is called hollow fan blades. Hollow fan blades. So the blade is empty with just a stiffener that is something like this. So you can see inside. I don't have a blade like this one here. This is an extremely expensive technology, but the blade is made out of two sheets, 1, 2, and a third sheet that is deformed inside in order just to give the stiffness. So you can see, you can look through the blade. So if you take this blade, here it's empty and you can see your hand on the other side. Of course, you see that thanks to the stiffener, you have increased the stiffness, and by the fact that it's hollow, you have largely decreased the mass. Of course, this is requesting extremely complicated manufacturing technologies. So this is absolutely requested that you use titanium, for example. It's only possible to build these blades using titanium, with some manufacturing techniques that are called superplastic deformation of titanium. I can explain you that if we have a few minutes one of these days. And the second big technology, this is to use composite blades. Composite blades that are made of carbon-carbon. So where you have fibers that are in carbon, and the matrix is also in carbon. And the fibers are made with some, let's say, special arrangements, because you are making some arrangements, some architecture of the fibers, so that you are going in two different directions, and you have like tissues that are already forming the fibers and giving you a stiffness in this direction and a stiffness in this direction. And so you are superposing these layers of fibers that have been prepared in this way. These are technologies like what you have in closes. And you are dropping inside these matrices of fibers the matrix, the liquid matrix of carbon. And this is solidified, and like this you have a carbon-carbon composite. And what is the problem? That, of course, it is with composites, so you will have a light solution, and by using some techniques in putting the fibers together in an organization like this, you are increasing the stiffness. But this is very complicated. There will be a video that will be shown to you. We will organize to show this video on the YouTube also. It's not a video that we have made ourselves, but we are not really discussing in this course the problem of certification. Certification of aircraft engines. But in the certification requirements, there is the bird impact, what is called the bird strike certification. And that means that you take a bird, and you eject, you drop, you launch the bird against the blade that are rotating. And composite materials are very bad for that. They are not good against impact. And so that means that on these blades, these are huge blades, you need absolutely to put on the blade, on the leading edge of the blade, a reinforcement that is metallic. So it's not a fully composite